When we think about electricity, we usually picture it powering our world through cables and wires. But what if I told you it can do so much more? That it can actually change the very stuff it flows through? Well, today, we're diving into the hidden chemical power of electric current.
We're all totally used to the idea of electricity zipping through metal wires to light up our homes and charge our phones. But what happens if you take those wires out of the equation? Can electricity actually travel through something like a liquid? That is the big question we're going to tackle.
Okay, so first, let's do a super quick refresh. At its heart, an electric current is really just a flow of charged particles. And in a solid, like a good old copper wire, those particles are very, very specific.
So inside every atom, you've got these heavy, positively charged protons that are basically locked down, but buzzing all around them are these incredibly light, negatively charged electrons. Now in a metal, these electrons are free to hop from one atom to the next, and this massive chain reaction is what we call an electric current. So if electrons are the key, how could that possibly work in a liquid?
All right, so how do we even find out if liquids can carry a current? Well, there's only one way to know for sure. We need an experiment, and we're going to use a pretty simple but really clever tool to see what happens.
Say hello to our conductivity tester. It's basically just an open circuit with a battery and a light bulb. The idea is simple. If we dip the two ends of the wire into something that can conduct electricity, it completes the circuit, and the bulb should light up. If it glows, we've got a conductor. If not, it's an insulator. Easy enough, right?
And this is where things get really interesting. When we test pure distilled water, absolutely nothing happens. The bulb stays dark. But watch this. We take that same water and just stir in some regular old table salt, and boom! The bulb glows, and it glows brightly. This tells us something pretty amazing. Pure water is actually a really bad conductor of electricity.
So that begs the question, what is going on here? I mean, it's still water. The electricity is still electricity. What is it about adding something like salt that just flips a switch and lets the current flow? What's the secret?
And here it is. Here's the answer. In liquids, it's not about those tiny electrons anymore. See, when things like salts, acids, or bases dissolve in water, they break apart into these much bigger charged particles called ions. And now, these ions, both positive and negative, are just floating around, free to move. It's their movement that carries the electric current through the liquid. They're the new delivery service for electricity. Okay, so we figured out that electricity can flow through certain liquids. But here's where it gets even cooler. The current doesn't just pass through without a trace. No, it actually causes a pretty profound chemical change. And this process has a name: electrolysis.
The name electrolysis sounds super scientific, but it's actually pretty literal. You've got electro for electricity, and lysis, which basically means to split apart. So we are literally using electricity to break down a chemical compound into its most basic parts.
And the effect is something you can actually see. When you put electrodes into water and run a current through it, you start to see all these bubbles forming. But that's not the water boiling. It's the electricity literally ripping the H2O molecules apart, releasing hydrogen gas at one electrode and oxygen gas at the other. It is a chemical reaction happening right in front of your eyes.
So how does this work? Well, it's like an elegant little dance of opposite charges. The negative electrode, called the cathode, attracts all the positively charged ions. At the same time, the positive electrode, the anode, is attracting all the negative ions. It's this orderly march of ions to their opposite charged electrodes that causes the chemical reactions to happen and keeps the whole circuit complete.
Now, this whole idea isn't just some cool experiment you do in a lab. This principle has massive industrial applications, and probably the most common one is something you have absolutely seen before. It's called electroplating.
Seriously, think about the brilliant shine on a bathroom faucet, or a car bumper, or even that affordable piece of jewelry that looks like it's solid gold. That beautiful, durable finish? A lot of the time, that's just a super thin layer of one metal that's been applied to another using the power of electrolysis.
The process itself is just ingenious. You take the object you want to coat, say this spoon, and you hook it up to the negative terminal of a battery. Then the metal you want to use for the coating, like this bar of copper, gets hooked up to the positive terminal. When you turn on the current, it starts dissolving copper ions from the positive side, carries them through the solution, and deposits them as a perfect, even layer onto the spoon. It's basically like painting with electricity.
So why do we even do this? Well, for a whole bunch of reasons. You can protect a metal like iron from rusting by giving it a coat of zinc. You can make things look way more attractive, like shiny chrome on car parts.
It lets us make affordable stuff look expensive by plating a cheap metal with a thin layer of silver or gold. It's even used to coat the inside of food cans to keep our food safe.
So we've clearly seen how electricity can cause a chemical reaction. But what if I told you it works the other way around too? What if a chemical reaction could actually create electricity? Well, check this out. This is a galvanic cell. And at first glance, it looks almost identical to the setup for electrolysis, right? You've got two different metals, some electrodes, a solution, but its purpose isn't to use electricity, its purpose is to create it. It does the exact opposite.
So think of it like this. It's a perfect two-way street. An electrolytic cell, the kind used for electroplating, eats electricity to force a chemical change. But a galvanic cell uses a chemical change that happens all on its own to push out electricity. It's this beautiful, symmetrical relationship between chemistry and power.
And here is the absolute best part. You use galvanic cells every single day of your life. We just have a much more common name for them: batteries. That little AA battery powering your TV remote, it is nothing more than a tiny contained chemical reaction designed to generate a steady flow of electricity.
So we have come completely full circle. Electricity isn't just a passive force that flows through things. It's a tool that can fundamentally reshape the chemical nature of matter. And in turn, that chemical nature can be harnessed to create electricity. It really makes you wonder, doesn't it? As we get better and better at controlling this amazing two-way street, what incredible new technologies are we going to unlock next?